Hello, students. Hi, I'm teacher Thaddeus Baluka, the ocean of chemistry and your chemistry mentor. Welcome back to my channel, whereby we try to unpack and make chemistry the most interesting and fascinating subject in the whole world. In our today's lesson, we are going to focus on a very important topic, and the topic of interest today is the topic of organic chemistry 2. We are looking at the alkanoic acid. So our topic of interest today is organic chemistry, and the subtopic is alkanoic acid. So the subtopic, as I've already said, we are looking at the alkanoic acid. We are looking at the preparation, that is task 1, preparation of ethanoic acid, and task number 2, we look at the conditions necessary when we're preparing ethanoic acid. We also need to look at the process. What is this process that is used in the manufacture of ethanoic acid? Specific objectives. By the end of the lesson, the learner should be able to describe the preparation of ethanoic acid and write chemical equations for the preparation of ethanoic acid. So let's look at the alkanoic acid. So one of the things that you need to understand is that now the general formula is CnH2n plus 1. Then we have the carboxyl group. The carboxyl group is the functional group. So the N here is 0, 1, 2, 3. So something that I want you to understand is that in methanoic acid, N is not 1, but it is 0, as shown here. So the N in methanoic acid is 0 and not 1. So that is when you're applying this formula. Like a student might wonder, but we know that the names of the organic compounds are derived from the Greek roots. And one of the Greek roots in the prefix there is meth. And meth means 1, meaning that methanoic should have 1 carbon atom. So with that kind of a scenario, I want to be able to unmask and try to unpack the secret behind that, or rather the rationale. First of all, we understand that the functional group in alkanoic acid is the carboxyl group. So the carboxyl group already has 1 carbon atom. So that is the rationale that in methanoic acid, the N will be 0 and not 1. So because the 1 of the carbon atom is already captured in the functional group, which is found, which is already taken care of in the general formula. So when you look at the ethanoic acid, et from the Greek root, it is 2. So the 2 means that ethanoic should have 2 carbon atoms. But when you're using the formula, we use N as 1. The rationale is because already, although we are using the N as 1, the other carbon atom is found in the carboxyl group. So finally, still ethanoic has 2 carbon atoms. So the functional group, which is the most active site, it is the carboxyl group. Why am I saying it's the functional group? It is the group, it is the group that makes that is responsible for the most of the chemical properties of alkanoic acid. So it is the most active site. So that is very much important. So alkanoic acid, their names end with oic, that is OIC. The general formula is CnH2n plus 1 COOH, whereby the N in methanoic is 0. So the N stands from 0, not 1. Very important. So looking at that, we can be able to look at this as you look at methanoic, the carbon is 1. So it is very much important that the carbon atoms are 1 because of the one that is found in the carboxyl group. Then ethanoic acid, you see the way we are opening the structural formula is carbon. So this carbon, there is a double bond here attached to one oxygen atom. There's another one single bond attached to oxygen and another single bond attached to hydrogen. So this carbon has 4 bonds, 1, 2, 3, 4. So I want to try to unpack some common blunders. Many students will pick this one as a student might pick this as ROH. This is not ROH group. This is part of the carboxyl group, which is written like C attached to 2 covalent bond, oxygen, then OH. So this is not a carboxyl. This is not a ROH group. This is simply the structure of carboxyl group. It is very much important for the student to be able to avoid that kind of a confusion. So that is how you draw for the ethanoic, the same. You have carbon, hydrogen. You have carbon, hydrogen, hydrogen, hydrogen. Then we have the carboxyl group as shown there. Then the chain continues for propanoic. We have the first carbon atom attached to 3 hydrogens, the second carbon atom attached to 2 hydrogens, and the last carbon atom attached to carboxyl group. That is now the one, that carbon atom is where the carboxyl group is attached. And now you can try to use the same scenario to be able to draw the structure of pentanoic acid, hexanoic acid, all the way to decanoic acid. Very important for you to be able to understand that. So let's look at the next, and we are looking at now our objective, that is now the preparation of alkanoic acid. So the alkanoic acid of interest that you are supposed to know how to prepare is the preparation of ethanoic acid. How do you prepare ethanoic acid? The preparation of the ethanoic acid through the oxidation of alkanols. So that is very much important for you to be able to understand that the preparation of ethanoic acid, should be through, or rather, preparation of alkanoic acid is through oxidation of alkanols. So it is to oxidize alkanols, and you oxidize alkanol using acidified potassium manganate 7 or acidified potassium dichromate 6. So we either use potassium manganate 7 or acidified potassium dichromate 6. It is added to specific volume of concentrated sulfuric acid. So you can you look at the sulfuric acid is simply we are talking about potassium dichromate 6 is added to a specific volume of concentrated sulfuric acid. The role of sulfuric acid here is to acidify. It is to acidify the oxidizing agent. So the mixture is stirred. So normally the procedure, you get potassium dichromate 6, you add sulfuric acid, then you stir until the potassium dichromate 6 dissolves in the acid. You have the solid now. So from there, the resulting solution is now acidified potassium dichromate 6. You can also be asked why that we don't use acidified, we don't acidify the oxidizing agent using concentrated hydrochloric acid. The reason is because the concentrated hydrochloric acid will now be oxidized by the oxidizing agent from chlorine gas. So now that will now be a different thing, because now we are going to have the acid now will be oxidized by oxidizing agent to chlorine gas. So now that's a different reaction, of which now the oxidizing agent should now oxidize the alkanol to alkanoic acid. So that's it. So there are 3 points that are very much important. First of all, the process of manufacturing these alkanoic acid, you need an oxidizing agent. So that oxidizing agent must be acidified. So that is the condition. And the process of preparation is oxidation. We normally prefer using concentrated sulfuric acid for oxidation and not hydrochloric acid, because hydrochloric acid, if used, will be oxidized to chlorine gas by the oxidizing agent. Capture that very well. Now, in the preparation of alkanoic acid, in our case, we are preparing ethanoic acid. Ethanol is added dropwise into the mixture while warming. So we remember from here, we have now dissolved potassium dichromate into sulfuric acid. Then you have started the mixture. So step number 3, the ethanol is added to the mixture of now the potassium dichromate or potassium manganese 7 and sulfuric acid. Then you add ethanol while warming until the mixture turns green. That is when you are using potassium dichromate. If you are using the potassium manganese 7, it will change from purple to colorless. So the concept is now during the oxidation process, the oxidizing agents are reduced. So the dichromate will change from chromium 6, which is orange, to chromium 3, which is green. So that is why the acidified potassium dichromate changes from orange to green. Number 2, if it is acidified potassium manganese 7, it will change from purple to colorless. Very, very important. Number 2, remember that now we are told now the mixture is known as now the refluxed mixture. The reflux mixture is then distilled and the ethanoic acid is obtained at a temperature of 118 degrees Celsius. So finally, you remember you're going to now distill because the mixture might even contain some components of ethanol and the acid. So you carry out the fractional distillation, whereby you'll be able to obtain pure ethanoic acid at a temperature of 118 degrees Celsius. So the points to note, the method of preparation is oxidation. That is the process that is used to manufacture ethanoic acid. We are using oxidizing agent, potassium manganese 7 or potassium dichromate, which must be acidified. So the acidifying of the oxidizing agent is the condition. Number 2, you may be told to state the observation. The observation, you focus on the color changes of the oxidizing agent, that if it is potassium dichromate, it changes from orange to green. If it, the acidified potassium manganese 7 changes from purple to colorless. That is very much important for you to be able to understand. And you can also be told how is pure ethanoic acid obtained from the refluxed mixture. And then you say it is obtained through fractional distillation. Now, let's look at now the chemical equations. And you're looking at this is ethanol. We are using the manganese 7. This hydrogen means it is acidified, and we're getting ethanoic acid plus water. Or somebody can the reaction mechanism is not needed here, but just know that now when you add acidified oxidizing agent, it changes from ethanol to ethanoic acid. The ethanol has only one oxygen atom, but this one has 2 oxygen atoms, meaning that oxygen has been added. That is oxidation. Looking at the other thing, we also have this hydrogen has been removed. This hydrogen has been removed. This hydrogen here. You can be able to see this is CH3, CH3. So this C has no hydrogen, but instead we have added an oxygen atom. So hydrogen has been removed. So removal of hydrogen is oxidation. So you can even be asked, give 2 reasons why you consider the reaction between ethanol and ethanoic acid as oxidation. So you can say because it involves addition of oxygen and also removal of hydrogen. Very important for you to be able to understand that. And then we have, if you're using dichromate 6, then it changes again. The reaction is still the same. The only thing is the color changes. So for this one, it changes the oxidizing agent potassium manganese 7 changes from purple to colorless, while this one, the acidified potassium dichromate 6 changes from orange to green. And remember, this is now the science behind the use of alcohol by the tropic policemen to be able to confirm whether drivers have taken a lot of alcohol. So the concept is now the alcohol is usually filled with acidified potassium dichromate 6. So when you are told to inhale, rather to breathe in, breathe out, so the alcohol content, if a driver is being tested, so if the driver has taken a lot of alcohol, then when he uses the alcohol, then they will be changing color from orange to green, and from there the traffic policeman will be able to confirm that you are ROH present because you have taken a lot of alcohol. So that's the science behind the use of alcohol. So the laboratory preparation of ethanoic acid, and we're able to see this now, the diagrammatic, the illustration. So here we have the water bath, we have the ethanol plus potassium dichromate 6 plus concentrated sulfuric acid. So the sulfuric acid is simply to acidify. So there are 3 reagents added there. So that is now ethanol, potassium dichromate 6, potassium, and concentrated sulfuric 6 acid. So in that kind of a scenario, we have the Liebig condenser to facilitate the distillation. So once now these ones are mixed and they are warmed, then we have the reflux mixture, which contains the ethanol and the ethanoic acid. Already the ethanoic acid has been converted to ethanoic. The ethanol has been converted to ethanoic acid. And to make sure that there is no ethanol that remains, we normally use excess oxidizing agents. So the observation during the reaction that now the acidified potassium manganese 7 changes color from purple to colorless, or the acidified potassium dichromate 6 is used, it changes the color from orange to green. To ensure complete oxidation, excess oxidizing agent is used. So you can even be asked why we use excess oxidizing agents. Very, very important. So you can even be told, name the reagents that are used in preparation of ethanoic acid. And you know, now you're going to say you need ethanol, you need acidified potassium, you need potassium dichromate 6, and you need sulfuric acid. So review exercise. So we have already looked at the main things. How do you prepare ethanoic acid? We have said we are using the oxidation reaction. We have also looked at now the observation, the color changes of oxidizing agent. The way I've explained, you can review the video. So now you're being asked to review exercise that is now relating on what you have learned in ethanol, that is alkanols. Explain why methanol is a liquid while propane is a gas at room temperature. So these are the questions that most of the students confuse and they give the wrong answers. And one of the answer that students give here is methanol as hydrogen bonding while propane as the van der Waals forces. That is not correct. Of course, the alkanol, they have hydrogen bonding in addition to van der Waals. The hydrocarbon, that is now the alkanes and alkynes, they only have the van der Waals forces. So both of these components have the simple molecular structure, but one of it has two types of intermolecular forces of attraction. So the correct answer there will be methanol has both hydrogen bonding and van der Waals forces, while propane only has the weak van der Waals forces. And that is why methanol will be a liquid while propane will be a gas at room temperature. So this question is synonymous being asked why methanol has a higher boiling point than propane. So look at the correct answer. Methanol has both hydrogen bonding and van der Waals forces. Those are the two intermolecular forces of attraction, while propane has the van der Waals forces only. Therefore, methanol has a higher boiling point than propane. And we have come to the end of our beautiful lesson today. Keep on following the Thaddeus Baluka, the Ocean of Chemistry YouTube channel. keep subscribing, and also comment, like and comment, and ask any question that you would like me to clarify on the comment section. You can be able to get a copy of the Octopath revision model or the top-notch book for further analysis and for smart and detailed and distilled notes. Until next time, bye-bye.